So you define a scheme, spec of A. So you started with a commutative ring with identity. From this you construct a topological space, spec of A. And we know that some kind of functions on this, that from spec A to different residue field, P belongs to spec A, you have, so any element here, you F here gives you a function, say F, which takes at the point P or at the point X, it is going to f of x, which takes values in A of px by px a px, right? The quotient field. This is your kx. So, but okay, before I define a sheaf on this spec of A, so this is a topological space, I want to define a structure sheaf. Like the case of variety, you define some sheaf of regular functions. So one should have such thing in the case of affine, in the case of spec A. And together with that spec A with that structure sheaf, you call it is a affine scheme. And what is a scheme? A scheme is a locally ring. I'll define what is a locally ring space. Locally ring space, which is union of affine schemes. So affine schemes are examples of locally ring space, and a scheme is like a locally it looks like a affine scheme. That means it looks like spec A with a structure sheaf. So. So there's the final goal, to define what is a scheme, abstract scheme. But before that, let's talk about what is a affine. Some example. Let's continue with some example. Affine n space. So in the case of a variety, you know that this is A n of k, right? But here you are not over just a field; you are over any ring. So you can define A n of z. So this is nothing but spec of z x1, x2, xn. In fact, for any ring R is any ring, you can define this is as spec of R x1, x2, xn. R is any ring of commutative. Any ring with identity. Commutative ring. So you can talk about the affine space. So for example, if R is to be the algebraically closed field, then the maximal ideals of this corresponds to the closed points of this scheme. So this is you see the dimension. I mean, it's all very general. I mean, it's see, once you can deal with any ring, it opens up a big thing. Okay, so here, for example, that Hilbert knows. So when R equal to k bar, that is k equal to k, when algebraically closed field, what you got in k bar, the maximal ideals here, the closed points here, closed points in A in k bar. This is nothing but the usual affine space, right? What you the affine the affine variety, affine space in the sense of variety. Right. Okay. For example, let's take A1K. Let's. So what it is? So you have the line, and you have this fat point, which is corresponds to this. Apart from the points, every point corresponds to a maximal ideal. They are close points, right? What are the prime ideals in K of x? So this is nothing but spec of Kx, right? K is, assume K equal to K bar. So then what are the maximals? So what are the prime ideals here? They corresponds to maximal ideals and also the zero point, which is a zero ideal, which is not the 0 point. 0 also is a point. I mean, the point 0 that also corresponds to a maximal ideal. That corresponds to x minus 0, not that one. But there is a 0 ideal. That's the fat point. So if I write it like this, so every point in, so there is this is the line K, but you have a big, the fat point, which is a generic point, correspond to 0 ideal. So the maximal ideal, this is the this corresponds to those maximal ideal, those every point here. So similarly, if in the case of A to K, say again K is algebraically close. What is this? So you have close. What are the points here? So you have the bunch of points in the plane. And what else you have? This is union to all kind of curves, right? The prime ideals. The prime ideals corresponds to irreducible curves, right? You have this curve, something like this. All curves, if you take any irreducible curve, that corresponds to a irreducible closed sub. You take a prime ideal, because that will correspond the union of such thing, right? And the point 0, which is a generic point, right? So not just close point, you have all the curves in. So in some sense that you have all the curves here, the generic point, because it is 2-dimensional, there are subvarieties. So in general, when you take a affine scheme of dimension n, say, then you have all the smaller closed subsets. Those information is also there. So this concept of a point, non-closed point, gives you that. So that's more information you have. Not just points, closed points, you have information about what are the closed subsets inside your topological space. So that's an advantage. Okay. So these are all open, closed sets. So what about open sets? What are the open sets? So open sets are complement of the closed sets. So for example, if I take any element in A, so suppose X is spec A, and if I take any element in A, then I can define a set D of F. This is a set of all prime ideals P in spec A, such that F does not belongs to P. Set of all points in spec A, as the F is not inside P. So this is nothing but that this is same as saying that you take the V of F, the ideal F, take all the prime ideals containing F, this is a complement of that, right? So this is a closed subset, principal ideal. I take the all prime ideal which contains this principal ideal and the complement of that. So this is the open subset. These are called distinguished open subsets or basic open subsets. In the case of variety, you have seen, right? It's you take D of F. These are, yeah, these forms a topology, the basis of a topology. So now here also this forms a topology. This forms a, these are called distinguished open subsets, or sometimes basic open subsets or distinguished. Basic. Good, but see, these open subsets are important in the sense that every open set contains this kind of sets. And to define, you have also done that exercise that if you want to define a sheaf on some topological space, it is enough to define it the sheaf on these open subsets. Then naturally you can extend the sheaf structure on any open set. We have the sheaf property, right? If you have function, if you restrict to some open subset, if you can cover it, if you have a function f, if you on some open subset, and if open subset has some subcover, and this is a basic open subset. If you don't know all this for df, then you know for the whole open set. So it's enough to whenever you want to define a sheaf on some topological space, it is enough to do it for the basis. If you know what is the sheaf, say sheaf of abelian groups or sheaf of rings, so it's enough to do it for this df. So that's why these are, for working purpose, these open subsets are very important, because that once you do it for this, then it's like you can extend it because of the sheaf property. And also another, it is like that whenever you want to give a map, say algebra map, say A to B, or vector space map from V to W, it's enough to do it for the basis element, right? Then you extend linearly. Exactly same thing here. I mean, because of the sheaf property, if you define it for this basic open subsets, if you know for that, you can somehow fill it over any open subset. So and so now X, so this is a basic open subset. So X is an open subset itself. X is spec A. So X, you can write it as union of D of Fi. So right, because X is an open subset, you can write it as union of. So then this is if and only if you can write 1 as summation AI Fi. Say but because that means this is that means there are finitely, when you write 1 as summation AI Fi, means there are finitely many, so that means it's quasi compact, right? So this is an exercise in Atiyah McDonald, that if you can write X as union of DFI, if 1 you can write it as summation AI. And you can have, for example, you can have two basic open subset and DG is inside DF. This is possible. This is if and only if G power n is in the ideal F. These are just checked. These are easy exercise. I will leave it as a check. Now you have a topological space. Now you can ask questions like when it is irreducible. Whenever you have a topological space, the first question you ask that when is it irreducible? So spec A, when it is irreducible. So irreducible component, they actually corresponds to minimal prime ideals. So in some sense it is irreducible if it has only one minimal prime ideal. So that's a yes, A is integral domain. Or in other words, the radical ideal or nil radical is prime. So this is irreducible if and only if the nil radical of R A is prime. Right? So and irreducible. So in general, irreducible components corresponds to minimal prime ideals. And when A is Noetherian, that means Spec A is a Noetherian topological space. This will corresponds to, so there are finitely many such components if A is Noetherian ring. In particular, when A is Noetherian, there are finitely many irreducible components. So this is about irreducibility. So now you can little bit weaken the condition that when it is connected, irreducible is connected, but connected is not irreducible. So I am saying that you can weaken the condition. So when Spec A is connected, if A has no idempotent, so if Spec A is connected, if A has no non-trivial idempotence. Idempotent means element like x square equal to x. Right. So for example, if I take two domains, say A1, suppose A1 is integral domain, and if you take A1 cross A2, product of two irreducible, A1 cross A2 is a ring, the direct product. A1 is a domain, A1 is integral, A1 A2 integral domain. So they are irreducible. They are irreducible, spec of A1 and spec. But if you take product, then this has idempotent, right? Non-trivial idempotent, namely 1, 0 and 0, 1. So this is not a connected. So spec of this is actually disjoint union of spec of A1 union spec of A2. So this is an example of a non-connect product of two ring. Yeah. So this is an example of a so, but now you can ask about the decomposition. Like suppose you have a topological space, right? And if you take some closed subset V of Z, V of A. So what is the in the components of that closed subset? So that's basically primary decomposition, right? So if I take some spec of A and if I take some closed subset, say Y, then Y you can write it as a disjoint union of irreducible closed subsets Y1, Y2, YR. So how this Y1, Y2, YR, so this Y will be V of A, right? And this A will be intersection of A1, A2, A, there will be primary decomposition. A is Noetherian ring. So then you can write it as A is some A1 primary decomposition. So then V of A will be disjoint union of. Now among them there are some primary minimal one. The minimal the corresponding prime idea, minimal prime. So they will be the component, right? That is how. So primary decomposition will give you such decomposition. I assume A is Noetherian. Yes, it has primary decomposition. So for example, if you take example, if you take to be A to be KXYZ and Y to be say V of FG. So F is suppose F of XY, F of XYZ. This is X square minus YZ, and G of XYZ. This is XZ minus X. Then Y this. So then you write Y as. So if you write this V of I, then I, what is the primary decomposition of I? You can check that this is nothing but XY intersection XZ intersection Y minus X square Z minus 1. So then Y is nothing but V of XY union V of XZ union V of Y minus X square Z minus 1. So these are the components, irreducible components. They are the prime ideal. These are the prime ideals. Okay. So now you have object Spec A, which is a topological space. Now the question is that what about morphism between such topological space? Suppose so one is that A to B, if you have a ring homomorphism, then that gives a map from Spec B to Spec A. Now you want, so this is a morphism as a set that you take the prime ideal in B and take the corresponding contraction phi inverse of P, which is a prime ideal. Now the point is that the topology you have given on Spec B, Spec A and Spec B, and this phi star is a continuous function. So that means what you have to check that if you take a closed subset in Spec of A, the inverse image of a closed subset is a closed subset, right? So phi star of inverse, so a closed subset is some say V of A in Spec A. This is nothing but V of, you take the image of an ideal, need not be ideal, but you have to extend it. So you take the extension of the image. So this is now phi star. Phi star is continuous because of this property, that phi star inverse of V of A is V of phi A the ideal generated by phi of A. And phi star inverse. So now similarly for the open subset, now if I take the basic open subset or distinguished open subset, phi star of df, phi star inverse of df, where af belongs to A, this is open subset. This is nothing but d of phi f. And now if you take a closed subset, it need not be proper in the sense that it need not be, it will not go to closed subset, but you can take the closure. So what is phi star of V of B closure? So naturally with the idea, how do you inverse image? You take the inverse image ideal, that's always an ideal, and take V of that. So this is, so these are the property of this function phi star. So first one makes the first one or second one makes the function phi star continuous, and the second one tells the how the closed sets, the closure of the image of a closed set. Huh? Inclusion. It will be inclusion. Huh? Yeah, but what is the ring structure for this? You have to give a morphism of ring, right? So you cannot say in general it is dominant, but if it is injective, A to B is injective, then it is dominant. So that's that is also a that if phi is surjective, then phi star is in a closed immersion. Spec A, this is a closed immersion. That means it's injective and the image is closed. So surjective means B is A mod A. So closed immersion, always you think like in the variety case also, the closed immersion also locally always look like this, right? Similarly here, phi is injective, then it's dominant. Phi star is dominant. That is phi star of spec B closure is spec of A. These are all given in Artier-Macdonald exercise, this first chapter. So example for this you can take A to A mod A, and here example is what? A to AF. Suppose you take the localization map. Always think this, that whenever you have dominant, this is the, I mean, because closure of AF will be A, because these are, assume A is domain, fine, that domain irreducible and all. If A is take A to be domain, and then this map, this is the inclusion map, A to AF, and spec of AF to spec of A, this map is a dominant map, because spec A is irreducible. 0 is a prime ideal.